Okay.
Share the screen. So actually this is lecture 3.1 because I realized that I was following a paper in which they are explaining Blanford and Janek process. So this will be a short lecture of just like, okay, what is a Kerr geometry and where does this Blanford and Janek process comes into the picture. And
Okay.
there are few details which I also need to know because I'm also like, studying this firsthand. So just to
Mm-hmm.
see what it is.
But
So
actually, I hope this is not like you had to prepare just to
no.
teach.
In any ways, it's fine because I was interested in these things like when I was being taught GR and all, and
Mm-hmm.
these are like good things to know, just to be sure.
Okay.
And
Mm.
recently, Sebastian came out with a paper on black hole flyby. So he wrote an educational paper. It's not
Mm.
in physics journal. It's a normal paper that an exercise could be given to general relativity students that if a particle is going inside a black hole, so how close it can go and come by. So he
Mm-hmm.
wrote a very short paper. So he was suggesting that maybe I can write an educational paper on Kerr black holes, like how will
Yeah, maybe.
particles move in that. And he said that obviously that you have to be careful that because this would be an educational paper and he said that these APJ or these physical review these guys won't take it, but there are these other journals which include these educational papers, so you can just write it. So that's why I am, anyways, I'm learning about Kerr geometry, so this is important.
Okay.
So, okay, so last time we had I'll just revise quickly. So we had like Newtonian gravity. Then obviously Einstein discovered the special theory of relativity, where space and time they came together. You can hear me, right? Audio is clear.
Yes, yes.
Yeah. So when special relativity came, space and time became one. And then the idea was that how gravity would be included into special theory of relativity. And then Einstein came up with general theory of relativity, which said that there is a geometry of space time which is bent by a mass being there, and that bend provides the geodesics which the orbits follow. So right now, Earth is around the geodesic around the sun. Sorry. And the first solution to Einstein field equations was Schwarzschild metric, which we had done last time. So Schwarzschild was a spherically symmetric solution for Einstein field equation. Remember that in Einstein field equation there was this important guys, this metric ds square.
Yes, ds square.
There are different ds squares. Or another word for ds square is the metric. So the
Mm.
main guy will always be the metric. So with
Mm.
one metric, you can study that, okay, what are black hole solutions? Or with one metric, you can study how the universe is expanding. So that is the Friedman-Robertson-Walker metric. Or with one metric, you can study that, okay, how gravitational waves affect space-time. So once the metric had come for a spherically symmetric mass, that was partial solution. Then the idea was that what if this mass is rotating? And then the idea came up across that, okay, you have a metric called the Kerr space-time. So that's how Kerr space-time came into the picture. So these were I mean, right now these pages which we will go through are just the basic notes which I took when I was studying this book by Blanford and Yannick. Not book, but there was this journal in which these two guys had published their first results. So
Mm.
some information might not be that relevant, but it's just okay to go through. And then
No,
in
no, it is. It's important to go through. Sometimes I would have just read and skimmed, but not like
Mhm.
at least gone through.
Yeah, so
But yeah.
right now I will just go through like few of the basics, and then in next lecture later on I will just focus mainly on Blanford and Yannick. So I
Okay.
mean, the basics of Blanford and Yannick is related to like these two guys. One is the what is called the Penrose process,
Ergosphere.
because
Mm.
the black hole is rotating, so the space time around it is rotating. So how you can extract energy from that? So that is related to Penrose process, and then there is a region in the Kerr geometry which is known as ergosphere. So we'll try to understand maybe these two things in like today's lecture. Okay, so this is stuck or what?
Okay.
Okay, yeah, so it's moving down, right?
Yes, yes.
Okay, so generally, in whenever we talk about black holes, then there are this is a surprising fact that there is a star, it lives through its life and it goes into gravitational collapse, but
mm,
at the end the object which is created, it has only these two parameters. So
mm,
whenever one is speaking about black hole, then there are only these two parameters to identify all the black holes in the universe. One is mass and one is spin. And how do you characterize the black holes on the basis of on the basis of how massive the black holes could be? Then the idea comes of how massive can the black holes be. So sort of first is that, okay, if the mass of the black hole is less than two solar masses, then these are called primordial black holes. So these are known to be born at the time of the Big Bang theory. And a more smaller version of these, the quantum black holes, were postulated to be formed in the Large Hadron Collider. There was this news that black holes might be created, but their lifetime was not even like few seconds. Then the majority astrophysical black holes, they lie in this mass. So it is like 2.2 solar masses to
it's
100 solar
200
masses.
solar mass.
So these are known as your stellar
Stellar.
black holes, and they are formed during the stellar collapse of stars, which are initially more massive than 25 solar masses. So stars which are massive than 25 solar masses, they undergo gravitational collapse and they end up as black holes. Then there are some black holes are which recently people are trying to figure out why there is a thing called mass gap. So the black
Mm,
holes which are detected by LIGO and Virgo are somewhere in between here. This has been detected, so this is fine. And
yes,
also at the center of the galaxy, you know that the M87 or the Sagittarius A star, we know that at the center of each
it's a
galaxy, it's
SMPH.
like the supermassive black hole. So these are
Mm,
like million solar masses. But then there is this intermediate massive black holes which
black
people are
holes.
trying to find out more about. And the next set of detections of LIGO, or I don't know, maybe X-ray astronomy, would be to find out more about these intermediate massive black holes, because then you would obviously have an idea as to how you go from here to here. Because I mean, because these masses which have been put that, okay, the upper mass is 100 solar mass, or here the lower mass is 10 to the power, how does this come into the picture? So people need to find out more about intermediate massive uh, black holes. So black holes are generally spinning object, and why do we know this? Is because uh, first of all, that these are caused by the angular momentum of the star. Because whenever a star and everything will collapse, so you can imagine that it has a spin and it has this angular momentum, and where will all this go? So it will go into the spin of the black hole, one can say. So these are caused by the angular momentum of the star or cloud that forms around it, particularly if the progenitor is a spinning neutron. It's easy that if you have a black hole and there is a neutron star revolving around it, so when it will collapse into it, it will impart its angular momentum to it. Then there are alternative other theories also that it could be formed directly due to during a supernova. So when a star explodes, it might happen that there is some asymmetric rotation which is left out, and that is acquired by the black hole. One might suggest like this. So right now we don't know. I mean, this is the major, let's say, the accepted theory that the black holes have the spins of the black hole is due to this region, but people are also looking into this region. Okay, and this is what I also read in their paper of Blanford and Yannick. Wait a
Mm,
second. This is not yeah. Actually, this was another book on. I can send you these books also, which I was referring. So these were like some research done like 30 years of Blanford and Yannick process, and some guy had written an article. So I was just picking out the important information from it.
okay.
So the original spin is certainly strongly modified by the accretion. So accretion is happening because the space-time is rotating around a black hole. The Chandra and the XMN Newton observations of the
So,
IRM atoms
mm,
in the hot gas orbiting a three solar mass black hole and of a handful of AGN have allowed to investigate the gravitational effects and spin of these black holes. So this paper which I am referring to right now was actually very old. So this is the basic idea where the research was going at that time. So they were, I think, looking into these iron atoms in the hot gas orbiting a black holes or few AGNs, and then they were trying to investigate what are the gravitational effects or the spin of the black holes. So what they found was that broad asymmetric uh, iron, this like I don't know
K
this,
alpha,
yeah,
yeah.
yeah, K alpha emission lines, they were found in the spectra of
Spectra.
both supermassive and stellar massive black holes. So I
Holes.
think these elements and all are obviously very important to depict what is happening at the center of these compact
Mm,
objects. So this is more towards the, let's say, the astrophysics part.
hmm. No, okay, but you please send me also this
Yeah,
paper.
yeah, I'll
It's
send you
important.
because this was
Hmm.
actually very nice. I mean, obviously I had no idea about like these things which I have written over here, but it
Uh,
was important to know that there were these iron atoms in the hot gas orbiting the
hmm.
orbiting the black holes, and people were studying the spectra of that. I haven't read about these things, so it was interesting. And then there was also this important thing that the gravity of a black hole, it shifts the X-rays from iron atoms to
Atoms
lower
to
energies, producing a
energies.
strongly skewed X-ray signal. Yeah, so this also was, I found it very interesting that how you have these signatures that okay, there are these black holes and everything. So it is, I mean, apparently, obviously, the gravity of a black hole is too much, so it can shift the X-rays from the iron atoms to lower energies, and it produces a skewed X-ray signal. So this was also interesting. And then there was this big equation which they had given, but I'll just go through it like just brush across it. So when people were trying to study it, they were trying to simulate the black hole magnetospheres. They were trying to understand that if the gas is in such a configuration, how much fast will it be accreted? So the black hole magnetospheres have been discussed in the force-free limit, and what was happening is that the magnetic field structure, which was represented by this asymmetric magnetic flux function, which was this. So this was
Hmm.
generally a solution of something which is called uh, Grad-Safronov equation. So it's, anyways, it was like you have general relativistic equations and
Hmm.
you just try to solve them, and in the end there are these differential equations all around. So this is one of the important equations. So in which this guy was important. So there was this asymmetric magnetic flux function psi, and that was sort of evolving. And you can understand right now that if there is a magnetic field around a black hole, you would want to know how that magnetic field is evolving, right? So
Yes.
when you do general relativistic calculation, this is the main equation which comes into the picture. And here we can see that in this equation, there are obviously the important, or let's say the usual parameters which one might expect, that there is the redshift parameter alpha of the curve geometry in BL coordinates. BL coordinates, I will tell you what they are. This is the cylindrical omega in this equation is the cylindrical radius. D is some function or something. But the important part was that the field lines they rotate. What you get after solving this equation is that the field lines, which is the, and this is the black hole and this is the accretion. So maybe these are the field lines or something. So these are rotating differentially with an angular frequency, and the polaroid and the polar and the, oh sorry, and the
Colloidal. Hmm.
colloidal current function is arbitrary in the force field limit. So at that time, I think this was one of the major equations which people were trying to find out. I mean, were trying to solve. And what happened was that, except for the Blandford-Yannick solution of this equation of slowly rotating roll, no analytical solutions are known. So while following this old book, it appears that this is the main equation maybe people are trying to solve at that time. And when you solve this equation in the slowly rotating case, then only the solution or the analytical solution which exists is of Blandford-Yannick process. And the basic idea was to have a picture of what a magnetosphere would look around a black hole. So this is the image also which I like took from that book only. So I told you that it's an old book. So here they were trying to say that, okay, if this is a black hole and it is rotating, there is a hot disk over here. So this was the global structure of magnetosphere, I think, which Blanford and Yannick got. So there are two important things over here. That first, the magnetic fields are advected from the parsec scale in an elliptical galaxy and embed the horizon into a spherical magnetic structure. So they were trying to predict that, okay, if in a galaxy there is this black hole, how will this magnetic field form around in a parsec scale in an elliptical galaxy, I guess. And then the plasma from the inner part of the hot disks, so this one region, is driven away and across the Alphen surface. I think it is this part. So I think next time I'll just try to go more in details about what they were talking here. But this picture was interesting, so I just kept it here.
Okay.
One interesting thing I found over here was in this process, what is happening is obviously that they need to solve the how what is the magnetic field profile around a black hole and all. But the interesting one side note interesting thing which I came across was this thing called magnetic braking. So I did not know about it, so I wrote it down because it was like pretty interesting. So magnetic braking is what? It is just a theory explaining the loss of stellar angular momentum due to material getting captured by the stellar magnetic field and thrown out at great distances from the surface of the star. So obviously there is a star, there is some magnetic field, it is attracting some particles towards it. So how it attracts the particles and it loses the angular momentum and it throws away the particles, or let's say gas in this case. So this is the magnetic braking. And what happened and why this is important and I also found useful is that the current expected theory of the solar system evolution states that the solar system originated from a contracting cloud, which
Yes.
which we know from Emily's talks, I guess.
Yes.
And here is the thing which I found more interesting, that as the cloud contracts, the angular momentum, denoted by L, it must be
And
conserved. So any small net rotation of the cloud will cause the spin to increase as the cloud collapses, forcing the material into a rotating disk. As the dense center of the disk, so at the disk center of the disk, a
yeah.
protostar forms, and
And
which gains heat from the gravitational energy of the collapse. As the collapse continues, the rotation rates can increase to the point where the accreting protostars can break due to centrifugal force at the equator. So this magnetic braking has to play a very important role during the, I think, the life cycle of a protostar. Because if this magnetic braking does not happen at a particular time, then the star can sort of break away. Our sun formed and her planets formed because this magnetic braking happened at a correct time. So I mean, for I found this was like very cool. Uh, so thus the rotation rate must be braked during the first 100,000 years of the star's life to avoid this scenario. This scenario means that the magnetic braking doesn't happen and the star just breaks away. And one possible explanation for this braking is the interaction of the protostar's magnetic field with the stellar winds. And this is one of the major theory how in solar system our sun was formed. So I was like very surprised that this fact called magnetic braking plays a role over here. And this magnetic braking plays a role in obviously how magnetic field evolves around a black hole. And yeah, so yeah, this was the paper which I was following by Blanford, Voiter, and Mayer. So they had written something
okay.
on AGN. So I have obviously written a note over here that it is an old book, so one has to be careful. So what they were doing is that they were solving electromagnetism in curved spacetime. So what happens? What does this line means? So remember that we had the Einstein equation. So we had this guy, G mu nu equal to 8 pi t mu.
8, yeah,
Yeah.
8 by
So yeah, this represents
team.
the space-time geometry, and this represents the matter which is causing that space-time geometry or something. So whenever you study this in vacuum, then you have very simple equation that in vacuum this side is zero. So these are vacuum solutions which are easy to solve. And now what happens is that if you want to study some form of matter, So this is obviously the stress energy momentum tensor, and you say that okay, what is the form of this stress energy momentum tensor? These are indices. So what it could be? So people generally say that okay, it can be a pressureless gas or dust or something. So what Blanford and Yannick did, so they considered this T mu nu as an electromagnetic stress energy momentum tensor, so which is given in form of the electromagnetic tensor. You
Field.
know this, right? F mu nu is del mu a nu minus. You're familiar with this, right? Or should I explain?
I mean, you had told in the first lecture.
Yeah,
I
so
have to
I'll
remember
just
the
revise.
equation. I
Yeah,
don't
I'll
remember.
revise over here. So this is the electromagnetic tensor, which is F mu nu. So this is
Mm.
generally given by partial derivative of a mu minus, yeah, a mu. What happens is that this depends on this vector potential. So this
Mm.
vector potential a mu, it has that as the time component, it has the scalar potential, which is phi, and the vector potential, which is a. And we
Mm.
know that your electric fields and magnetic fields. So as far as I remember, magnetic field is given as the curl of the vector potential,
Yeah,
and electric
del
field
crossing.
is the gradient of
It's
phi
of the
minus del A by del T. I mean, this was the question which used to come in net and all. So you can see that all this electric and magnetic field I can represent by the vector with the four vector potential, and with the four vector potential I have the electromagnetic tensor, which is called F mu nu. And how you can put this in the left hand side of the equation, there is an equation called uh, it's written in my board over here, I forgot what it's called, but you can sort of form it over like this: F mu nu F kappa nu minus of G mu nu F alpha beta F alpha beta. So this is your whole T mu nu. So generally, so this is the
for
T.
electromagnetic
Yeah.
field.
So
Yeah, okay.
this is called the electromagnetic the energy momentum tensor of the electromagnetic field. So
Field.
this F mu nu together is called the stress energy momentum
Mm.
tensor of the electromagnetic field, which has the electromagnetic tensor like this. So if you put this equation on the if you put this on the left hand side of G mu nu equal to T
Mu,
mu nu,
T
and
mu.
then when you
Okay.
solve the system, so what does this physically represent? It says that there is a space time, some
Mm.
curved space time, and the energy content present in the space time is an electromagnetic field. So this is what Blanford and Yannick they had solved in this is the equation, and these were the few things they found that up to 29% of the mass of the black hole is extractable, which is the Penrose process. And
Mm.
in short, what they did was just this line that they solved the general relativistic version of Maxwell's equation in a Schwarzschild metric. So G mu nu equal to 8 pi K mu nu. I told you what T mu nu was. It
Yes.
was that F mu nu guy, and you can
Mm.
see that they have solved in a Schwarzschild metric.
Metric
So the ds
means
square,
non-rotating black hole.
yeah,
Okay.
non-rotating. So here the ds square was the one which is 1 minus 2 gm by blah blah. That goes
Uh,
into here.
okay.
Once you will solve this together, you get what is called the general relativistic version of the Maxwell field equations. So once you solve this, you will have that how particle behaves in a curved space-time where obviously you have electric and magnetic field and so on. And then now yeah, so this is the Schwarzschild geometry, which is the non-rotating case. So Schwarzschild geometry, what it does that it describes the space-time geometry outside a spherically massive object characterized by its mass. Okay, but most of the astrophysical objects they are rotating. So since an object is rotating, this isotropy is destroyed because the rotation of the axis it defines a special direction, because once an object is rotating, you know that it's going to rotate around this axis. So what happens is that your form of the metric or the ds square it changes. So uh, Actually, it becomes a bit more complicated, which I'll show you later. But what happens is that once you are forming this metric, there's things to realize that this is the general form of a stationary axisymmetric metric, which is like this. Now, the thing to realize over here is that you can see that there is this term called d phi and dt whole square, right? Since it
Hmm.
is whole square, there will be a term called dt d phi. So I have just
Yeah,
yeah.
DTD5. Yeah, it'll be.
So I have written these terms like this. So these are the
Hmm.
important terms. So if I'm saying that, uh, I'm saying that okay, what is this GTT term? So remember that this is the metric G mu nu, and these are the terms I'm talking about. So generally
Hmm.
TT is this part. So you can see that there are two T's over here. So the TT part has obviously a term, and also there would be a dt square, right? Because you have to square this. So this would be a minus b omega square. So you can see that GTT term is like this. Similarly, you have a GT phi term, G phi phi term, and GRR term. So even if you don't solve the whole metric right now, you can still sort of guess what few things are happening. So what is happening here is that, yeah, so this presence of this term, which is this thing, GT phi, this actually results in a thing which is called frame dragging. So frame dragging happens that even if you are still and you are going towards a Kerr black hole, no matter what you do, you will start to rotate around it. So this is called your sort of frame dragging. So I think so I mean there is a bit of maths which I think I'll go later, but important thing is that you have the space-time metric which we were just doing, that you have this GT phi term and everything. Means when you will do the maths and all, you will see that a particle dropped in a straight line from infinity is dragged just by the influence of gravity so that it acquires an angular velocity. So this is called the dragging of the frames, dragging of inertial frames. This does not happen in Schwarzschild geometry. This happens in Kerr geometry. Why? Because the time and the phi component are sort of intertwined with each other. So this is generally what is happening, is that at t is equals to 0, you will have a space-time like this. But as
Hmm.
t increases and when you fall into a black hole, your space-time grid changes. So you can see that there is some form of rotation happening. And this is
Yeah.
unavoidable. This is because this is there inbuilt in the solution. And now what you do is you obviously plug this equation into the Einstein field, you plug this metric into the Einstein field equations and try to get the form of the metric, and the metric you get is this, which is the Kerr geometry.
Hmm.
And as you can see that it is pretty complicated because there are
Yes.
these big terms coming and all. And every metric can be written in a particular coordinate form. So this form of metric which you are seeing right now, this one, this is called the Kerr metric in the Boyer-Lindquist form. So this is the
Linguist
BL
form. Okay.
coordinates which I was talking, and this is the, one can say, the most used coordinate system when one is studying the Kerr geometry. So
But okay, now, okay, one thing is, even though we use a Kerr non-stationary black hole solution,
mhm.
and we see the, what I mean, basically the electromagnetic field lines around it, and it just seems that they're a rotating black hole. I mean, you get the solution of a rotating black hole.
Yeah, here Kerr geometry is not implying any magnetic field or electric field, because this is just representing the space-time of a spherically symmetric object which is just rotating. The
Hmm.
magnetic field and everything people can. So now what you can do is you can have this ds square, which is the Schwarzschild metric, which is the
Hmm.
left hand side of the Einstein equation, and now on the
Hmm.
right hand side you can study, you can have some electromagnetic field and something.
Hmm. Hmm.
Because what Blanford and Yannick had done, that they had this equation 8 pi mu.
8 pi.
What they did is that they took the ds square, the metric of Schwarzschild,
Mm.
And then they added the electromagnetic field tensor.
Okay.
Now, what
Okay.
obviously I
Okay.
think which people have done and what is generally done in the computers and all, because you take the whole differential equations and you can put it into the what
Mm.
to say into the computer. So this is what is called as general relativistic magnetohydrodynamics. So when people are talking
Mm.
about general relativistic magnetohydrodynamics, so you have the ds square, which can be of, I mean, which what can be? It's usually of curve because you need the rotation part, and then you add the f mu nu, which obviously is the right hand side. So I
Mm.
should write it again because this is not correct. So yeah, you have the left hand side of the Einstein field equation g mu nu, which represents the space time geometry given by whatever you want. You can have ds square. Then you have the right hand side of the Einstein field equation, which consists of the matter you want to study. We know that we want to study how electric and magnetic fields are behaving. So we have this thing. And the two metrics which we can have is the Schwarzschild or the curve. So
Yes.
the general relativistic magnetohydrodynamics codes and everything, what they do is they take the Einstein equations, they have the curve metric on the left hand side, they have the electromagnetic field on the right hand side, and you put it into a computer and you get
Mm.
your codes. And that's why you get those, though you know,
Movies. Yeah.
yeah,
Yeah.
that movies and all. So important thing to just see over here is that, okay, where is this metric blowing? So
Mm.
one can see that if this rho is equals to 0, this would be 1 upon 0 infinity. So this is also sort of blowing up. If
Yes.
this delta is equal to 0, it is also blowing up. So generally what happens is that in Schwarzschild, when you study, the metric is singular at a point. But when you study that what are the singular points for a curved black hole, you see that it actually is a ring. So
Mm.
this is a bit weird part over here, that the metric is singular at rho equal to 0 and delta equal to 0. You can look into the equations. And this, when you solve this, because this rho is actually this factor like this. And once you will solve this, you will get two values of R. So
Mm.
this means that the singularity in a Kerr black hole is in the form of a ring. So this is very different from obviously Schwarzschild black hole. This is obviously a mathematical situation, that what is happening inside the horizon, but the metric tells us like this. And so this is the basic picture of a Kerr black hole which you study. So this is the ring singularity over here. Then there are two event horizons. So one is at r equal to r minus and r equal to r plus. They are there in the equation. Then outside these two horizons is the region called ergosphere.
Sphere.
And this is the region where the space-time is rotating and your magnetic fields and everything are sort of rotating. And it is here that you can have the process called the Penrose process, by which energy can be extracted from the rotation of a Kerr black hole. So, in
Oh, oh,
yeah,
but this ring is it the innermost uh, stable orbit, like which you were also saying in your?
no, 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 that is not because
Oh,
the
okay.
innermost stable orbit is obviously outside the horizon. So
Hmm.
for a Kerr
Oh
black,
yeah.
yeah, for a Kerr black hole, if this is the horizon at r equal to 2m, then the
Hmm.
innermost stable horizon is outside, is over
Hmm.
here.
Hmm.
Similarly, in Kerr space time, if this is the, let's say, yeah, obviously not, let's say if this is the horizon, because this is the outer horizon over here. So there are some particle orbits which would be somewhere like this outside the horizon, which would be
Hmm.
the innermost stable orbits. So those would be there.
Okay.
So
This is nice. Like you summarize so fast, but
yeah, I had, because I mean, because the problem is that uh, in my talk also you saw that interstellar, when you solve the Schwarzschild black hole, it's sort of simpler, but when you have
hmm.
to solve this equation over here,
Hmm.
it's it's really complicated. Um, you can see it's like pretty weird. Not weird because when once you start with a metric with these properties, And once you reach over here, there are some
mm,
complexities which you have to take into account. And the new feature you are getting from a schwarzschild black hole is first that the event horizon is not a point but a ring. And
mm.
second, just because this object has a spin, there is an effect called frame dragging. And frame dragging is the one which is the rotating of the, what do you say, rotating of,
Magnetic field lines.
yeah. And also if you take a small gyroscope or something in this region, so you can actually measure the spin of the black hole.
Wait, gyroscope is. I
Gyroscope
forgot what
is that,
gyroscope is.
that instrument which measures the, which gets affected by the rotation of the earth.
Oh, Earth.
Yeah. I mean,
Wait, I'm.
it's, you can see that there are these cool videos where a guy has a rod and he has that instrument and he gives it a pull and it starts to rotate like this. I'll send you the links.
I may have seen it, or I'm getting. Is it like sextant? No,
No, no,
no, it's not.
no, 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 not sextant.
Okay, now I'm